All right, so before we start the lecture, are there any general questions about project 2, course logistics, homeworks, any material from last time? Okay, everyone's all set, so everyone knows submit your projects and topics by Monday. All right, so why don't we start today's lecture? So today we are going to continue our discussion of sampling, aliasing, and resolution, and hopefully wrap that up, and then start a discussion of RF excitation and slice selection. And then those will be sort of the core material we need to get through, sort of, so you have a full understanding of generally how MR works. And then after that, we'll start revisiting sort of relaxation and contrast, and talking about how you can create different types of images with MR. Okay, so last time the main topic was this picture here, where we're talking about K-space sampling. And so the basic picture is that, okay. So in image space, the user is going to specify their FOV in the X direction and the Y direction based on how big the object is. They're also going to specify the resolution, okay, and basically how small they want each voxel to be. And so obviously, if you're scanning something like a human brain, a typical resolution will be about 24 by 24 centimeters. That covers most human brains. And then a resolution might be anywhere from, typically a standard resolution for anatomical imaging, about 1 millimeter isotropic. Okay. But if you really need to go faster, you might be willing to trade off and say, well, I don't really need 1 millimeter. I'm okay with 2 millimeters. I'm okay with 3 millimeters. And so that's one of the trade-offs you might make, because the higher resolution you need, the longer time the scan may take. Now, in a future lecture, we'll talk about tricks to get beyond these limitations. But for now, these are the limitations we have. Okay. And then the field of view is going to determine your delta x, your delta kx, and your delta ky. And the resolution is going to determine your W, Kx, and your W, Ky. All right, so that's really the fundamental relationship that we'll take a look at during the rest of this lecture. So as you saw in your homeworks, or hopefully seeing on your homeworks, if you don't sample finely enough, you get aliasing. So we obviously want to sample finely enough to avoid aliasing. And so we ended up with these Nyquist conditions. So for sampling, we want 1 over delta Ky to be greater than the FOV. Okay. And so for any design problems, you can just set that greater sign to equals. And so you can always say delta Kx is just equal to 1 over the field of view in the X direction, and delta Ky equals 1 over the field of view in the Y direction. So that's your first 2 sets of design equations. So on the pre-lecture quiz, I think most people got that. If you're given the field of view, which is the size of the object, delta K is just 1 over that, all right, and vice versa. So that's a fairly straightforward computation to make. Now, before I go on, there was the problem that sort of seemed to give people the most problem in the pre-lecture quiz was the interference. I mean, so just say one word about that. If you did not get that correct, you can always go back and plot what your answer was and sort of convince yourself why that wasn't the correct answer. So for example, if you selected 1, 3 in K space, you draw that, then you would end up with an interference pattern like that. Okay, and that's not the right angle interference pattern that was in the image. So so basically, if you did not get that right, then it's not a bad idea to sort of plot where you are in K space and just draw the perpendicular to that vector and just see what pattern you would have gotten. All right. The other problems people did pretty well on, so I'm not going to go over those. That's basically an application of those design equations, and so they're fairly straightforward. So if you didn't get those, just sort of check and see whether you. It's important that you know how to apply these. So if you have any questions, please ask. The next thing we talked about was windowing. Okay, and windowing refers to how far out in k-space we go. And the way we determine that is we have a windowing function. And since we multiply in the Fourier domain, we are going to convolve in the image domain with the inverse transform of our window. So typically, for this course, just for the basic stuff, this will be a rect function, and then therefore this will be a sinc function. Right? So we're going to be convolving with sinc functions, and the width of the sinc function determines your resolution. So shown here. So we know that if we have a sinc of wkxx, so this corresponds to a rect that has width of wkx in the Fourier domain, then this has an effective width of 1 over wkx. Okay. So the design rule is we would like 1 over wkx, that resolution, that width, to be less than my desired resolution. Okay. And that's the same as saying that wkx should be greater than 1 over my desired resolution. So now this is the other design equation that we want. And that makes sense because if given desired resolution, it's okay if I collect more data in Fourier space, right? Because that's only going to increase my resolution, right? But if I collect less, then I'm going to get a bigger width, and that's not going to meet my resolution requirement. It's always okay to acquire more data. Similar with delta K, it's always okay to sample more finely. Then you just get a bigger FOV. But the cost is time. Okay, if I make WK too big, then it takes more time. If I make delta K too small, it also takes more time. So I don't want to, even though there's a greater than sign there, I don't want to go too far beyond that boundary. Right? And so generally for any design problem, you can always just say WKX. We're just going to set it equal to 1 over delta X. So to sum up, what we're doing is we have some desired Fourier transform here. We're going to sample it with a cone function that has spacing of delta kx, delta ky. So these are sampling at that intervals. And then we're going to multiply by a rect function that has these two widths. Okay. Since this is multiplication in this domain, we're going to convolve in the other domain. So we convolve with a cone. And this has spacing of 1 over delta kx and 1 over delta ky. And then we're going to also convolve with this two-dimensional sinc function. And so this was the example we went over last time. So I'm not going to go over it today, but essentially just showing multiplication in one domain, convolution in the other domain. So here are our final design criteria. So we have the criteria on delta kx, and as I said before, you can just make that equals, and then wkx can also be equals. Okay, so it's actually fairly simple to remember. The things we give you are FOV and delta x, or somehow you figure out what those are, and you take 1 over those to get the desired components in k-space. Question?
Sorry, what's the physical representation of the delta x and delta y exactly?
Sorry, what is delta
x and delta y exactly?
You mean delta k? Oh, delta x? Oh, delta x is like, if you have your image, right, it would be like the resolution volume. So delta x, delta y, like the size of your pixel. Okay, so if you go back, for example, to this, it's, whoops. How do I get rid of that? All right. It's basically this resolution size. So essentially your pixel size. Yeah. Any other questions? Okay, so let's take a look at this. This sort of describes everything. So I have my kx axis here, my ky axis here. Okay, I'm going to sample with a spacing of delta kx along this dimension, delta ky along this dimension. The width is wkx here, and the height here is wky. And then I've also added these things. So this means that this is kx max is the farthest out I go in k-space on the plus, and minus kx max, assuming symmetrical, is just the opposite of that. Okay, so kx max would just be equal to wkx over 2 in this case. Okay, just the farthest frequency I sample. And similarly, ky max and minus ky max are shown here. Right? So these are the sort of the terms you'll see bandied about as we're thinking about how to design the pulse sequence. So what we want to do is we want to build up, we're going to spend some time sort of reviewing this, and then we're going to go through an actual design of a pulse sequence for MRI. Okay, so before we do that, let's look at this problem here. So once going to open up the poll online, and then for those of you in person, we'll just do a voice poll. So here's the question. This is my object now. So it's I think this is the same object we had last time, but now the question is different. So we have a cosine 2 pi 3x plus 2y, rect of x over 3, rect of y over 4. So now it's your sort of, what you want to think about is what would be a reasonable choice for the resolution here. Given you know you want to image this object, what resolution should you pick? And once you have that desired resolution, what are the kx max and ky max parameters needed to achieve this resolution? And the multiple choice is just asking about the kx max and ky max. All right. Any questions on that? If not, let me open up the poll online, and then if you're in person, you're welcome, obviously, to do the poll online too, but you can also do a voice poll. All right. So we'll give about 2 minutes for you to think about this, and then we'll go over it together. Okay, so go ahead and submit your answer online if you're online, and then basically I'm going to close my eyes and count to 3, so I'm not going to see who's saying what, so then you can just yell out what you think the answer is. All right, so I'm closing my eyes. 1, 2, 3. Okay, so I heard mostly C's and 1 D, which is very similar to the online poll. So 70%, 73% said C. What's changing now? 71% said C. 14% said D, and 14% said B. Did anyone in the room say B? Okay, so yeah, that's about right. Okay, so I probably heard B, C, D, so it's about right. So probably C and some B's and D's. Okay, so let's take a look at this. So this is an object here. So this we saw last time, that determines the extent of your object, right? So assuming you don't really care too much about the edges, you know, then what really determines what resolution you care about is the frequency of variation in this cosine. Okay, so the quickest way to do this problem is just to look at this and say, well, this just has the form cosine 2 pi kx x plus ky y, right? So what's kx? Just 3, right? And ky is equal to 2. So that's the frequencies in my object, right? So I should probably at least sample that far out, okay? And so 3 and 2 would be the minimum I would need to sample that, right? Because I would be collecting that frequency. That's the highest frequency I would be sampling, okay? So that's one way to look at the problem, okay? The other way to look at the problem and to sort of work it towards more what we just talked about is if you imagine, let's look at cosine 2 pi 3x, right? Okay. So the setup has kx equal to 3. Okay, so what is the period of this? What's the period of that cosine? Yeah, 1 over 3. Okay. So if we drew that, that means that it would look like something like this, right? Where this period is 1 over 3. Okay. So what would be the spatial resolution you want to be able to represent? What's the minimum spatial resolution you want to be able to represent that cosine for the period 1 over 3? What should your delta x be? 1 over 6, right? Because you've got to be able to at least sample the peak and the other peak, right? So positive peak, a negative peak, a positive peak, a negative peak. So that's the resolution you'd want. So you want delta x equal 1 over 6. Okay. And therefore you'd want wkx equal to 6. And then kx max, which is equal to wkx over 2 equals 3. Okay. So those are two ways of doing that problem. All right. Any questions on that? Okay. So this is showing you what it would look like if you sat down at, in this case, it's a GE console. So every vendor has a different console. So if you sat in front of a GE MRI system, this is what you would see. All right. So let's talk a little bit about what is specified here. So some of the parameters some parameters we've looked at. So the flip angle we've talked about a little bit. That's how much, so we zoom in on that. The flip angle is how much you're going to tip the magnetization. Okay. Echo time, we really haven't talked about too much. We'll talk about that in a future slide. Bandwidth, we'll talk about a little bit here. This is 125, so essentially 125 kilohertz. Notice here, we've got FOV. Okay, so in this case, 24. So it's understood that's 24 centimeters. So in this case, the technician has specified they want a 24 centimeter FOV. And slice thickness is 5, which we'll talk about later. They've said, I want a 5 millimeter slice with an FOV of 24 centimeters, all right? Now, they haven't specified resolution here, right? You don't see any resolution here, right? So instead, and different scanners are different, but instead what they've specified is matrix size. So this is the number, frequency stands for the readout direction. So this is the kx direction. Okay, and this is the ky direction. Okay. So in this case, delta x would be equal to, my FOV is 24 divided by the number of voxels or pixels I want in the kx direction or the x direction, all right? So that's 256. All right, so in certain scanners, most scanners actually you'll specify the matrix size as opposed to the resolution. Okay. And then here, the phase FOV is 1. That just means as a percentage of the other FOV. So this is FOV of X by definition. Okay. A lot of things you just have to know depending on the vendor how they define things. So you wouldn't know this unless someone told you. But for GE system, FOV is specified in the X direction. Okay, the readout direction, and then this is just what fraction of that readout direction is my phase FOV. So this means FOV of y is equal to 1 times 24. Okay, so that's the fraction. So then I can say that delta of y equals 24 divided by my metric size in the phase direction, which in this case is 128. Right? So that's what happens. So the person sits down at the scanner, enters these values, and then we're going to talk about the computations that go on behind the scenes, assuming that this, let's see what, can we tell what sequence this is? Let me see what sequence this is. Yeah, this is so you can see the subject is lying supine, so they're lying on their back, okay? And interestingly enough, their feet first, okay? So generally we put in people in head first if we want to image their head or their body, but their feet first, so they're probably gonna image their knee on this one, okay? And the coil, oh no, maybe not. It's an 8-channel cardiac coil, so I'm not sure why they're feet first. And the 3-plane localizer means that we're going to be scanning 3 planes, boom, 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 just quickly to see where the heart is or where the brain is, right? And what else? Yes, there's the pulse sequence, so we'll talk about that later. And so basically, this just gives you an idea of sort of what, yeah, so you can sort of see here, they're showing the person's going feet first, right? So this basically gives you an idea of sort of what goes on from the technician point of view. And then now we want to transition a little bit into what goes on from the engineer's point of view. Okay, so we're going to use the spin warp pulse sequence to go through this. And so remember the spin warp pulse sequence collects line by line by line phase space. And so for each line, we use the phase encode gradient to change our position in KY. In the GX direction, we're always doing the same thing. We're just going out to the left, zooming back to the right. We're going to minus KX max and zooming across to KX max, right? And this is the RF pulse that's just tipping the repetition at a repetition time of TR. And we'll talk a little later about why this is important when we talk about contrast. So this is now the basic spin warp pulse sequence. And so if you were to, as you saw, if you watch the bagpipe video, what would happen is if you were lying in the scanner, the gradients make sounds. And so you would hear boom, 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 each time the line is being acquired. Okay. So what's happening in K-space, you can sort of see the KX transition is the same each time. It's going negative KX max here and then zooming across to KX max. Takes you, once again, going down to minus KX max and then going up to KX max. Okay, so it's linear progression across KX space. Here, the KY has a different job. It takes you out to some initial position and then just holds it. Some another initial position and just holds it. Okay, so that's the offset in the KY dimension. So now we're going to sort of get into the guts of what's actually going to happen. So we're going to talk about how sampling is actually done. Okay. So how does sampling actually happen? So there's 2 different types of sampling. The sampling in the KX dimension for spin warp is different from the sampling in the KY. So that's a special characteristic of spin warp pulse sequences. Now in your homework, you're going to see things that this doesn't necessarily apply to. So one caveat is sometimes students try to take spin warp pulse sequence and apply it to other sequences. Now the fundamental design rules apply, but you can't just take one approach and just morph it to another approach. So just be careful that you're not trying to take what we're doing here in class today and just change it a little bit. So this only works really if there's one dimension that's sort of fast, okay, and the other one that's slow, all right? So the readout direction is what we call the fast dimension, okay, because we're just zooming across K-space. Okay, so imagine this, it's the fast dimension because we zoom across it each time, right? So that's the fast dimension. The KY is the slow dimension because we have to wait and acquire line by line, okay? So there's a difference in terms of which is the fast dimension, which is the slow dimension. The fast dimension, the sampling is very quick. We sample that electronically. So the way it works is, this is the RF signal that the coil sees. We demodulate it. So we multiply by a mixer. We mix it down with a cosine at the RF frequency or the Larmor frequency, and a sine at the Larmor frequency. And let's assume our isocenter is omega naught, right? So what that does is, this is a real signal, right? This is an actual signal in the real world, right? that we're just measuring. You can look at it with an oscilloscope. Now we're multiplying it by cosine and sine, which are 90 degrees out of phase. So we're actually creating an imaginary number from that now, right? So this is like, we're going to create something like I plus JQ, all right? Where I and Q are the in phase and the quadrature components of that signal. So we're creating an imaginary number. So we have two streams here. We can apply some low pass filtering, and then this ADC stands for analog to digital converter, which is basically, I mean, every one of you has one in your pocket right now in your phone, okay? That didn't used to be the case. Most people did not have their own personal analog to digital converter, say 20 years ago, but now everyone has one. Because every time you do anything in your phone, it's taking analog input and converting to digital so it can beam into the web. Right? So you probably have more than one ADC actually right now on your phone. Okay. There's probably one for your audio, one for your video. And there might even be one for your magnetometer that you use. Okay. So you probably have 3 or 4, I would imagine, in your phone right now. So what that does is it basically samples the incoming waveform at some sort of interval every delta t. It's going to take a sample. Okay. So it does 2 things. It samples, it also quantizes, right? It has to assign a number to that. So we're not really going to talk about quantization in this course. We'll assume the quantization is good enough, but the part we care about is the sampling part. So this is what it looks like. So the delta t is how often we're acquiring a sample in k space along the kx dimension. Now that happens as a function of time, right? This axis here is time. Okay? And this is the ADC playing out. And what's happening is, as this is happening, we're only sampling when it's crossing k space. Okay? And so we're acquiring samples in k space. And so the question is, how far do we move in k space in each delta t? Because that's going to give us our delta kx. And the good thing is the answer is pretty simple. Delta kx is just gamma over 2 pi times the area that we accumulate in some delta t. So that's just the size of this gradient, gxr, times delta t. All right? And so you can sort of see, if I give you the FOV, right, then you can figure out the delta kx. And then you can if I give you one of these other parameters, then you can also figure out the other parameter. So let's take a look at an example of that. Let's say I give you the FOV in the x and y direction is 25.6 centimeters. Okay. And delta x equals delta ky equals 0.1 centimeters. So the first thing you should do whenever you look at a problem like this is the first thing you want to calculate is, okay, well, what's my matrix size? How many voxels am I going to have in x, y direction? Because that's something good to keep in mind. Right. So for this example, what would be my matrix size? Right. So I think if I'm hearing the whispers correctly, it's 256 by 256, right? So very easy. But that's good to keep in mind, because if you're coming up with numbers that are like in the 2000s or the millions, I'm getting that's wrong, right? I need to get something that's like 256 by 256, right? Okay, so let's look at this. So we said that FOV of x is just 1 over delta kx, which is this. In this case, I'm given that delta t is equal to 32 microseconds. And so I can solve for gxr by just plugging in these things. And I get in this case that the size of the gradient I need is 0.28675 gauss per second. Okay. So that means if I know I'm sampling every 32 microseconds, then I need to play out this gradient to get the correct delta kx. Right. So that's a fairly straightforward design. Now let's look at what we have to do in the how many samples we need to acquire in the WKX. So that's the readout duration. So how sub x here is how long is the gradient applied for? Okay. So remember, we're acquiring samples with some delta t, right? So without even doing any math, but knowing the matrix size, what should you guess is the size? What should tau sub x be? I mean, we can obviously do the math, but if you were lazy and didn't want to do the math, what would be a good guess of how long, in terms of delta t, what should tau sub x be? Any guesses? Should it be 10 times delta t, 20 times delta t? How many samples do we need to acquire in kx, given the fact that we know our image has a certain matrix size? Yeah, it should be 256, right? So we're going to guess that it should be equal to 256 delta t. Okay, because we know we're going to create an image that has 256 points in image space. So unless we do something really cool and tricky, we're probably going to need 256 points in Fourier space. Otherwise, we're getting something for nothing. Later on, we'll show how you can sort of get something sort of for nothing, but for now, you can assume that that's what you need. All right. Okay, so let's look at this. So you're given delta x, so then you can figure out what wkx should be, right? And that's equal to 2 times kx max, right? But it's also equal to just the area of this whole thing, right? Because the area of this covers how much you travel from one part of k-space to the other part of k-space, okay? So this whole area, gamma over 2 pi gxr tau sub x, will tell me what my wkx is, right? And so therefore, let's look at this thing here. So delta of x equals, we just said it's equal to 1 over wkx. Remember, this is just wkx. Okay? It's just the area under that readout gradient. Right? And so, and we solved for gxr before, right? So we can just solve for tau sub x. So tau sub x equals 1 over, we have our delta x here, we have our gxr. You can go and plug in this and you get, it's 8.192 milliseconds, okay? And it turns out that this is just the number of readout samples you're going to acquire times delta t. And this number turns out to be 256. Okay, so just showing that this is a nice sanity check. So if you were in a rush and you didn't have time to do all this algebra, although it's not very much, you know, your guess would have been pretty good, or would have been correct. Right? So that's the readout gradient. Any questions on that? Okay. So if there's no questions, then what we can do is we can do another quick poll just to make sure that people are on the same page. Let's see, I'm going to relaunch the poll here. Okay, so this is the question. You're asked to design a spin readout gradient to achieve an FOV of 20 centimeters and a resolution of 2 millimeters. Okay. The maximum gradient strength you have available is 2 gauss per centimeter, and the readout sampling period is 5 microseconds. So this 5 microseconds is the delta t. Okay. What should be the amplitude of that readout gradient? And then you may assume that gamma over 2 pi is 4,000 hertz per gauss, so your calculation should be very simple to do. Okay. So go ahead and take a minute to look at that. You can talk, obviously, feel free to talk to your neighbors, whatever it's. And we'll regroup in a couple of minutes. So when it says pick the closest answer, that just means the correct answer may not actually be there. So just pick the closest one. Okay. Okay, about another minute and then we'll regroup. Okay, so go ahead and answer your question online, and I'm going to close my eyes, count to 3, and just sort of yell out what you think is the right answer. Okay, 1, 2, 3. Just say something. No answers? Okay, well, your people on the people on you're competing with the folks online, so they've already answered. So go ahead, come on in people. Just say your answer. 1, 2, 3, go. A. Okay, great. Points for participation. Who said A? Yeah, 5 points for participation. Okay. All right. All right. So yeah. So let's see. It was fairly uniform distribution online. The most popular answers were B and F. Okay. All right. So we have a pretty shy in-person group. So let's go through it in person though. So you're given delta t, so that's really important, right? So that's a big thing. And you're also given FOB, right? And we saw from the example from those two alone to figure out the gradient amplitude. So this is one of those problems where there's a lot of information thrown at you, but not all of it's necessary to solve the problem. Okay. So we know that delta kx is just equal to 1 over the field of view of x, right? So we can have 1 over 20 centimeters. And we know that's just equal to gamma over 2 pi times the gradient that I want times delta t. Right? So I should just be able to write down delta t there, or gxr is simply equal to 1 over 20 centimeters, right? 4,000 hertz per Gauss on the other side, right? And then 1 over 5 times 10 to the minus 6, right? So now we just have to solve for what that is. Okay. So obviously, if you're doing this, you know, wherever you're at, I mean, you can just use a calculator to do that, right? But let's do it the old-fashioned way. See, this 1 over 8 times 10 to the 4 times 5 times 10 to the minus 6 equals 1 over 40 times 10 to the minus 2 equals 100 over 40 equals 2.5 calories per second. Okay, so F would be the right answer. So as you can sort of see, the calculations are actually pretty straightforward. Okay, the tricky part is realizing what's the information you want. Right? So everyone can do that calculation, but maybe it wasn't clear which information you want. So are there any questions about that? Because this is the type of calculation you'll be expected to be able to do on homeworks and quizzes, right? Okay. So if there's no question, we'll move on to phasing code. And we'll look at the sampling now we're going to look at sampling in the KY dimension. And remember, we go line by line by line through KY. And so now the delta KY is determined by two things. One is tau sub y, which is how long we have the phasing code gradient on for. And then this GYI, which is sort of the incremental amplitude that we increment by each time we step by, okay? So it's just sort of this incremental gradient GYI, and that's delta KY. And so given FOB of y, we can always figure out delta KY and then solve for one of these two things. Okay, so let's take a look at this. So in this case, we know the FOV. We know the FOV is 25.6 centimeters, so we'll use that later. So we know we know the FOV. In this case, you're given that tau sub y equals 4 milliseconds. All right. And so now you're just asked to solve for GYI. So you can just sort of take the GY over to this side, take the FOVY down here, and you solve, and you end up with this a very small gradient, 0.00224 Gauss per second. Because you just increment, it's just the incremental gradient you need to move a little bit in case space. Now let's look at the resolution in the y direction. So this is sort of talking about how far out do I need to go out in case space. And so that's the delta y is going to determine the delta kx, and that's going to be 2 times kx max. And so that you can write that as gamma over 2 pi, 2 times GYP tau y. So what is GYP? GYP is the largest gradient you're going to play out in, say, the positive direction. Okay. So this gradient, if you play out something of this gradient, it's going to take you out to ky max, right? And similarly, if I played out the gradient in the opposite direction, it would take me to minus ky max. So here's an example of that. We have our delta y, and we are solved. So here's the 2 times GYP, because we need twice that to get my width in k-space. I've given tau sub y, so I can just solve for g sub yp, and I end up with 2.868 Gauss per centimeters. And it turns out this is just np over 2 times gyi, which is the size of each increment. And so this number here, if I have 256 samples, right, I've got to go 128 one way, 128 the other way. So this number here would just be 128. So it turns out if you actually go and solve for things, you'll find out that that's 128. Okay, any questions on that? Okay, so putting it all together, this is what happens with the spin more full sequence. So we have the readout gradient looks like this, okay? And so the key things are delta t and the size of this gradient. And this tau sub x simply is just the number of samples we have to acquire times delta t. So we can sort of see that we would definitely use FOV of x to figure out delta kx. Once we have delta kx, right, then we can solve for either GXR or delta t. And similarly, if we have delta x, we can solve for GXR and tau sub x. But we already know GXR from here, and tau sub x typically is just going to be the number of readout samples times delta t. So this in many cases, this calculation can be sort of redundant and just more of a sanity check. Similarly, with the Bayesian code, if you have some FOV, that determines your delta ky. And so you have gamma over 2 pi, GYI tau y. That's how much each one of these little increments moves you in k-space. And similarly, for the resolution, you have to figure out how far in k-space you need to go. And then these two things tend to be related by the number of samples you need, which is also dependent on the matrix size. So these two calculations are also somewhat redundant in the sense that if you're acquiring full Fourier space, then they're going to be related by sort of the number of samples you. Okay, so for a spin warp full sequence, you're asked to design phasing code gradients to achieve FOV equals 20 centimeters and resolution equals 2 millimeters. The maximum gradient strength available is 6 Gauss per centimeter. What is the minimum width you can use? Okay, so I think it's actually worth doing this problem, just because now it's sort of a different design thing where you're asked for a minimum time to use given a maximum gradient. So go ahead and do that. It take another minute and then we'll regroup. Okay, great. So let's talk about this. So we've got some good response online. Anybody in the room want to say something? C. Okay. Any other choices? What? B? D. Okay. So that's pretty much in agreement with online. So C and D were 44% each. And then one person who answered very quickly said A. Okay, so let's see. So there's someone online who's answering these like in 10 seconds. So probably watching last year's videos. Okay, so let's take a look at this. So I think this is a good problem to go through because now this is sort of a slightly different design criteria where you're looking for a minimum width, okay? And this is actually very applicable because in MRIs, we talked about time, things are always decaying away. As we'll see next week, the signal is decaying away very quickly. And so we're always trying to move through k-space as quickly as possible before we to capture that signal. So whenever we can go as fast as we can, we want to go as fast as we can. So when we play out this gradient, so it's saying we have 6 Gauss per centimeter, right? So we're going to assume we want to use that whole gradient strength, right? We don't want to waste that. If someone says I can go I've used 6 Gauss per centimeter, I'm going to use all that gradient strength. So for this one, we're going to assume that we're going to use the full gradient strength. You know, so minus 6 Gauss per centimeter in that direction, okay, to get us out to some initial point in k-space, right? The job of this gradient, right, is to move us out to some point in k-space. If we want to use the gradient, the full gradient, that's going to move us out to that far point in k-space, okay? And so then we're trying to figure out what this tau is. So now that we know we want to move way out in k-space, what do we care about? We care about the width of k-space, right? So now the relevant parameter is not FOV, but it's resolution. Okay. So it means that my answer has nothing to do with FOV now. Okay, because I'm trying to figure out how quickly can I get out to the edge of k-space, and how far I need to go out depends on my resolution. So my delta y is equal to 2 millimeters, or 0.2 centimeters. Okay. So I know my WKY is equal to 1 over that, so that'd be 5 inverse centimeters. All right. And the other thing I know is, you know, minus 6 Gauss per centimeter just gets me half of that. And so I know that I can just imagine if I go from minus 6 to 6, that's 12 Gauss per centimeter. So I can sort of imagine that's the area I want to cover. So I can say gamma over 2 pi times something that's 12 Gauss per centimeter times my tau has got to move me 5 inverse centimeters. It's got to move me from one end of k-space to the other end of k-space. All right. And so now I just solve for tau, right? So it's 5 inverse centimeters over 4 times 10 to the 3 hertz per Gauss divided by 12 Gauss per centimeter. Okay, so let's see what that equals. That's like 5 times 10 to the minus 3 over 48, right? So that's approximately 1 times 10 to the minus 4. So A would be closest answer. Okay, because 1 times 10 to the minus 4 is about 100 microseconds. So you sort of see, depending on what you're trying to optimize, in some cases you're going to look at FOV. That will get you the answer. But in this case, FOV would not have gotten you the right answer. You have to look at the resolution. All right. Any questions? Yes.
Can you explain how you got 12 Gauss per centimeter over time?
Sure. So 12. So there's 2 ways we can do this. One is we can say the 6 Gauss per centimeter gets me to KY max, right? So I could just say KY max is equal to WKY over 2, which is equal to 2.5, right? Or but if I don't want to take that extra step, I could just say, well, actually, I want to go from minus to plus. And so I could just assume I'm using 12 Gauss per centimeter. That swing is 12 Gauss per centimeter. Yeah. Okay, any other questions before we move on? So we're actually going to skip this in the interest of time. And we're going to talk a little bit about some sort of practical things that are good to be aware of. But these are more just for general knowledge, and then we're going to start a little bit of our expectation. So here's one thing that sort of puzzles a lot of students is assume I have, this is my field of view, okay, and I want to have basically 1, 2, 3, 4 voxels. So this would be 1, 2, 3, 4 voxels, right? So it seems like, you know, the samples I can imagine having 1, 2, 3, 4, 5 lines if I want to get the center voxel. So the idea is, you know, I have, let's say I have some FOV and I have some resolution unit delta equals FOV over 4. Okay. Then the idea is, you know, how many how do I create my image? Do I have 1 here, 1 here, 1 here? So that's 1, 2, 3. Then do I acquire this image? Do I acquire that voxel, or do I acquire that voxel to get my 4? If I'm assuming I'm centered around 0. Okay. And it's the same question in K-space. Do I select these 4 or these 4? Okay. It turns out that this line and this line in K-space are the same. Once you have certain FOV and a certain resolution, it's just that one is going 180 degrees each time positive, counterclockwise, and the other is going 180 degrees counterclockwise each time. And so it turns out it's the same amount of information. So what that means is oftentimes when you're looking at something like that's like 256 by 256, right? Then typically you would think, oh, I need, the 256 doesn't, if I have the 0 line, then it's not going to be symmetric, right? I have a 0, then I'm going to have 1 here, and I'd have 127 above and 128 below, right? So it's not going to be symmetric. That's okay, because the line that you missed, that information is acquired by the line that you acquired because of that plus minus pi thing. So that's sort of, if you see something where, hey, it looks like they're missing a line in K-space, it's just because of that ambiguity. Okay. I'm not going to go over this. This just sort of goes out into a little more detail. The other part we want to talk about is windowing. And this is a little bit related to CT, where you look at the Ramlack filter and you look at variations of the Ramlack filter. So in MR, we have a similar thing where anytime you have a very sharp edge, okay, so imagine you have a very sharp edge here, right? What we said is in image space, we're taking our object and we're convolving it with a sinc function. Okay. So anytime you take a sharp edge and convolve with a sinc function, you get what's called Gibbs ringing or Gibbs artifact. There's a ringing around the edge. And so the question is, so here actually in this image, you can sort of see quite a bit of that Gibbs ringing. Okay, so all these things here, these lines here are not in the image. Okay, and so if you acquire more, if you convolve with a finer sinc function, then these tend to die off much more quickly. They're the same size in terms of the size of the ringing, but they die off much more quickly. And so from the point of view of the image, they're much harder to see. Okay, so this is one trade-off you might make, but now the cost is you've had to acquire more samples in K-space, and maybe you don't want to do that. Okay, and why is this important clinically? You know, imagine you're like looking at some cartilage, or you're trying to look at someone's knee, an MRI of the knee, and you've got this bone, right? And then if there's ringing into the cartilage, it might look like, if you don't know that's Gibbs ringing, you might think, oh, maybe the cartilage is damaged because it's got these dark spots in it, right? So knowing what artifacts are is very important for the radiologist, because radiologists have to be able to sort of what's called read through artifacts. They have to say, oh, this is just probably an artifact. It's not really in the anatomy, right? so therefore I can ignore it. But they have to be pretty sure about that, because if it really is a problem and they just say it's an artifact, then they've made a misdiagnosis, right? So radiologists tend to be sort of the sort of the physicians who actually have to have a little more technical knowledge than the normal MD, because they have to be able to understand what's an artifact and what's not. Now, eventually, and there's a big debate whether AI will take over that and be able to figure this out. But I think at least for the next 10 or 20 years, radiologists will still have a role in terms of at least managing that. Okay, because AI, until we're convinced that AI is good enough, there's still a lot of human knowledge that's available. Okay. The other approach we can take is instead of using a rect function K-space, we can use like a Hamming window. Okay, similar to some of you played around with, like, sort of a RAM lac, you could sort of taper off that in CT. And so what this does is it sort of has a smooth transition. So it doesn't kill off the high frequencies immediately, but it smoothly tapers them off. And you can sort of see, instead of a sync function now, you have this nice smooth function. Okay. The trade-off, though, is that now instead of this sort of sharp transition, you're going to sort of smooth out that edge. Okay. So that is a trade-off that you may or may not want to make. So typically on scanners, there will be a little button you can press that says like filter in K-space, and this is what that's for. But there's always a debate. Each site might have a different choice. Like some radiologists will say, I don't want any filtering. I just want to see the image as it is, artifacts and all, because I know I can read through them. If you're in an area that maybe there's not so much expertise, then maybe you would want to turn on the filter, because maybe there's not enough medical expertise at that site. Okay. And the last thing I want to talk about before we move on to RF is something that's sort of interesting, which is that we know it takes time to, once you have the field of view, the bigger field of view you have, right, then that means delta K is smaller. So you have to acquire more samples, right? And that's going to take time. So the question is, well, if I have, say, something really long like a spine or a snake, which should be the readout direction, which should be the phase encoded direction, and then how do I deal with aliasing? So it turns out the answer is you should always put, where possible, the long axis should always be the x direction, or your kx, okay, your readout direction. So readout is always along the longest aspect of your object. Okay, because think about it this way: if you're trying to image someone's abdomen, right? This is all you care about. Let's say you just care about their lungs, right? But the actual FOV is their whole body, right? So how do you avoid their head folding into their lungs, or their thighs folding into the lungs, right? You can't just chop off these parts of their body and just image that. Right? It was a cadaver, you could, right? But a live human being, you want to be able to say, I just want to image this part of the body and not have these parts fold in to my image. So it turns out the way to do that is this has to be the readout direction. Okay. And let's talk a little bit about the reason why, because the reasoning for this is actually going to be exactly the same reasoning that we apply for slice selection. So we actually have two options. One is we can put this along the readout direction. And here's the thing. So this is, say, someone's body here, right? And let's say all I care about is I just want to image this region here. Okay. But there's the whole body. So how do I avoid like the heart aliasing into the head? Right? I don't want an image of someone's head with a heart in it. Okay. So here's the idea. When I apply this readout gradient, right? Remember, a gradient makes protons at different locations spin at different resonance frequencies. So these are going to be spinning at some frequency, and if the gradient's positive, they'll be spinning faster. They'll be spinning slower, and these guys will be spinning really slow, right? Because they're even in a part where the gradient is stronger in a negative direction. So I know that the spins I care about are in some frequency range, right? And I know these spins are outside that frequency range. So what if I could just filter, just only take the signal within some filter, some bandwidth? And it turns out on the readout direction, the signal's coming in and I can filter it just using electronic filter, okay? And so that turned out to be the solution, that on the readout direction, you have this option where you can filter the data So you're only getting spins within some region. And so that's why the low pass filter in the readout direction helps prevent aliasing. Okay. So that's this low pass filter here. Okay. So what that means is, let's say my object is this, okay, and this has this field of view, like that's the whole body. I can have my filter that says, well, I only care about spins in a certain region. Okay. And so then when I multiply that in the Fourier domain, it's only going to keep the information in that reduced FOV. Okay. So that's sort of one thing that is good to know when you're sort of wondering how would you actually every image a long object without having to sample the whole thing. Okay. So that's one solution. The other solution is, well, if I only care about this part, what if I just only excite the spins in this part? Okay. So all the other spins are not excited, so they're not going to be processing around, and they're not going to contribute to our signal. So that's the other solution. Just excite what you care about and measure that, and everything else is not going to contribute in terms of the signal. And so that's slice selection. Right? But the same principle, we're using the fact that spins are different frequencies to only select to excite the spins we care about. All right. So are there any questions? So we're finished with our discussion of sampling. So are any questions or things that were confusing before we move on? Okay, if not, we're going to now transition to RF excitation, which is essentially, first we're going to review a little bit of what we mean, and then we're going to talk about slice selection. And I think for today, we're just going to try to motivate it, and then on Monday, we'll maybe do some problems to sort of look and see how that works. So remember, excitation is the process of taking the magnetization away from its equilibrium point and tipping it away. Okay, in this case, we're going from equilibrium and tipping at 90-degree flip angle. And so remember, we saw this picture. The key is we have to apply RF pulse on resonance. And if we're on resonance, then we can get that magnetization to go away from its equilibrium point. The very important point is if we're not on resonance, then the magnetization is going to be left alone. So that's going to be a clue, right? If we can deliver the spins we want to tip over the frequencies they want, then they'll tip over, and the spins that don't have the right frequencies are not going to tip over. That's how we're going to do our slice selection. Just to remind you about laboratory and rotating frame. You know, it's much easier to think about things if we're rotating along with the RF pulse. So in that frame, the magnetization doesn't spiral down, it just comes down like this. So it's easier to think about. Right? So we will want to look at things in the rotating frame. And then just remind you that the key is things will always process around whatever field they have. So if the field is here, it's going to process here. If the field is here, it's going to process around this. So whatever the net field is what they're going to process around. Okay. So I'm just going to talk you through this. So this is basically, we've talked about the block equation before. Now we're going to introduce, just at least give you an introduction to this thing, what's called the rotating frame block equation. So now this is saying, okay, in the rotating frame, how do things act? And it turns out everything is the same. It's M cross B, but now it's a B effective, saying in the rotating frame of reference, there's an effective field. Okay. Now the effective field is given by this notation. It's the B that we're applying, okay, plus this omega rotation term, which looks like a 0, 0 minus omega. Okay. So B rotation is actually the B field that we're applying that's rotating around. Okay. And then we've got this additional term here. Okay. So the idea is that if we want to think about this, what we'd like to do, if we're on resonance, then the B effective should just be this just this field that we're applying. Okay, so if we're rotating around, right, then this is rotating around. But once we're in the rotating frame reference, it's steady, right? This is the B field we're applying. And so if we're on resonance, then this B naught field, we can ignore it, right? Because we've sort of things are not going to process around this anymore. They're going to process only around this rotating field. So they're just going to go like that. And that's the key. When you're on resonance, that B0 field, it's almost like it disappears, okay? Because it's sort of like when you're on a merry-go-round, right? Once you hop onto the merry-go-round, it's as if there's nothing causing that rotation. You know, you're in that frame of reference, so you don't see that rotation. So what happens if, let's say you apply rotating field, that's a B1 field along the I hat direction, and then you still have this B0 field, okay? So the field that's being applied is this big B0 field, uniform field, plus this teensy little field along the I direction. So in the K direction, you have the strong B0 field, and you have a small little field component in the I direction. Okay. And the idea is we want to make this part go away. And in the rotating frame, this part does go away because we have B0 minus omega over gamma. And then if omega equals omega naught, which means we're on resonance, then it means in that rotating frame of reference, the overall rotation, we don't see that anymore. So this is as if that B0 field is not there. So then our B effective is simply this B1 field that we've applied in the I hat direction. Okay. So we talked about flip angle before, and we had some exercise on that. So flip angle is just omega 1 times gamma B1, and then the integral of that gives you the flip angle. So here's the idea behind selective versus non-selective excitation. All the spins are in equilibrium magnetization. So far, we've talked about non-selective excitation. We're assuming we're going to tip all the spins over, right? But then, like, if you have a whole body, then all those things contribute to your image, and then you might get aliasing, and you may not want that. So what we'd love to do is be able to say, leave these spins alone and only tip these spins. Okay, so now you can just make an image of a slice, right? What that looks like in this dimension, so M sub z is uniform, and there's no transverse. With selective excitation, now the M sub z is unperturbed here, but it goes to 0 here, assuming a 90-degree flip angle in the slice. And then within the slice, you get full magnetization in the transverse plane. So this is what you'd like to do ideally. And remarkably, you can come pretty close to this in practice. So the way you do that is we're now going to introduce something called gamma GZZ, where it's going to introduce a gradient. Okay, and this is what we talked about. If we can make spins at different locations have different resonant frequencies, then those spins that don't see the right frequencies are not going to get tipped over. So now if we're on resonance, now we have our B1 term as before, but each location has this additional gamma GZZ term, which means that it's gonna effective field is not just this, it's gonna also have a component along the K direction, which is going to cause things to not process around this, but process around something like this, okay? And if it's way here, it's just gonna stay up here. So it's not gonna get excited, okay? And that's shown here. If I apply a gradient, the effective field is right where we want it at the isocenter, but as we go farther away, the effective field points up because we've added enough, the gradient has added enough field, such that the spin's gonna process around this, and it's not gonna be excited down to where we want it. Okay. So that's fairly abstract, right? So let's talk about a little more real world example of this. So this is what's called a Barton's pendulum, which I only discovered about 5 years ago. YouTube is great. I mean, you can, things that you've never even seen before, all of a sudden you discover. So we're going to play this video, but let me explain what you're going to see here. So you've got these pendulums and they're of different lengths, right? And you remember from like physics, right? There's like square root of L over G or G over L, I forget which it is. So the resonant frequency of each pendulum is proportional to the square root of its length, right? So these pendulums have different frequencies of oscillation, right? What the person's going to do is they're going to set one pendulum swinging. So I think they're going to set this pendulum here swinging. So it has a certain resonant frequency, right? So the question is, which one of the other, what's going to happen to these other ones, right? Are they all going to start swinging, or, so this is essentially like a gradient, right? We have a gradient of frequencies here. So these are, you can think of these are different spins, each spin with a different resonant frequency, right? So the question is, how will these other spins react? So let's take a look at that. So right now, it's sort of, nothing is happening yet. They're just sort of random motion. I think at some point, the person is going to come and grab this one. Yep, there he goes. And so that's now my RF pulse, right? That's the driving resonant frequency. And sort of see, it's sort of exciting all of them now. But as time goes on, I think it's this one that's moving the most, right? So I think that's pretty cool. So that's basically what an MR exit, if you have a gradient applied and you apply an RF pulse, that's essentially what's going to happen. One spin, the spin at the right resonant frequency will be tipped over, and the other spins will not be as affected as much. Okay. Now you still see they still are affected, so it's not a clear slice that we've got, but it's sort of getting us there. Okay. So now we're going to talk about how we actually do slice selection. And the logic behind this is exactly the same thing we talked about when we talked about using the readout direction filter. So imagine you have someone's head and you only want to select a slice in their head like here. I want to take one slice in their head and just image that. So if you apply a gradient, there's going to be some bandwidth of frequencies, right? There's going to be some frequency here and some frequency here, and then there's going to be frequencies outside of that. Okay, so this will be a higher frequency, a lower frequency, and then much lower frequencies. All right. So the idea is if you want to excite all these spins in this slice, you better give each spin its own frequency, right? So you need to come in with a pulse that has a range of frequencies. Okay. And in fact, the spectrum of your pulse should probably be a rect function, right? This is a function that, as a function of frequency, will deliver equal energy at every frequency in that bandwidth. Okay. And then this is centered around some omega naught, but around that center frequency, you want a uniform bandwidth. And if you can do that, then it means that each of these spins in different parts of your slice, they'll all get tipped over. Okay, because you're giving each one of them the frequency they need. And so it turns out that if you have a rect function in the Fourier domain, that means you're going to apply a sync pulse in the time domain. Okay? And so this is exactly what we do in MR. If you go to any MR center and look at what pulses are being played out from an oscilloscope on a transmitter, you're going to see sync pulses most of the time. Now, there are more fancy pulses, but I'd say 90% of the things you're going to see are sync pulses. Okay? So that's pretty cool because it's sort of this mathematical sort of entity, but it's used practically, every day, all the time. Okay, so we're gonna let's see, what are we gonna do? Yeah, let's just walk through this and then we'll review it on Monday, but just to give you a sense of what direction we're gonna go. So we want to actually have build a little bit of intuition in how do MR engineers design these pulses and what are the trade-offs they make. So let's assume you want a slice profile of this form, rect Z over 10 millimeters. So that means you want something that, eventually you're going to excite something that is a 10 millimeter slice width, okay? Or 1 centimeter slice width. Okay? And you're given an RF pulse that's sync T of T, where T is equal to 400 microseconds. So the question is, what amplitude pulse can you use that will excite that slice for you? So let's think about how to do that. So let's see. What is it? Sort of amplitude of the slice? First, let's just do this one first, and then we'll do the other one one day. So the question is, what should be the slice select gradient to use? Okay, so we know we want to apply a gradient, and slice select is typically by definition the Z direction. Okay, so we always call the slice direction the Z direction. So it's going to be a function of Z, and so that gradient is going to determine the thickness of the slice. Okay. So let's look and see how we would go about calculating that. So we know we want a rect function with some bandwidth. Okay, And that bandwidth has to cover all the frequencies within some delta Z. And we can figure out that bandwidth as so. We say the bandwidth is equal to gamma over 2 pi times GZ delta Z, right? Because this will tell me sort of the frequencies that are covered within some delta Z. Okay. Because you remember, frequency is just going to be gamma 2 pi times the B field, right? So this is basically bandwidth equals gamma over 2 pi times the delta B that I need, okay? Or the delta B that I'm creating. I create that delta B with GZ delta Z. The bandwidth of this, if I have a rective F over BW, it will transform into sinc of BW times T, okay, ignoring leading scaling factors. And that can be written as sinc of T over T. So whenever you see sinc of T over T, this is just 1 over the bandwidth of the pulse. Okay, or this bandwidth of the pulse is just, yeah, that. Okay. So I know the bandwidth is equal to 1 over T. And so therefore I can solve. I can say, well, I know T, I know delta Z, so I can just solve for GZ. And in this case, I get 0.587 Gauss per second. Okay. So the idea is that once the T specifies the bandwidth of the pulse. So once I know the bandwidth of the pulse, I can say, well, I'm going to set my gradient amplitude such that over some delta Z, I get the same bandwidth. So it's just a matter of setting bandwidths equal to each other. Okay, so I think that's all for today. So we'll regroup on Monday and pick this up again on Monday. So I guess the homework is due Friday at 5. So you have Friday at 5 to do that. I will post the next homework today though. But you'll have till next Friday to complete it. And I think people agree that you can still submit it next Wednesday if you want to be done before Thanksgiving, but we will, there seemed to be general agreement that it was okay to give 2 extra days to do that. All right. And then make sure you submit your project descriptions and groups by Monday. So we can start that. Okay, thanks.